Hi everybody, welcome to one more of Mrs. John's lesson. This is for Year 13 Physics, Mechanics, and I am looking at banked curves but where there's friction involved, and how do you solve a problem when there's friction as well. So what I have here is the diagram of something going around a curved path, but the surface of the road is not flat, but it is banked at an angle. So the forces acting on the object, there are three of those forces. So there's gravity force acting vertically down, where Fg equals mg, and that is at right angles to the horizontal. That's your surface of the road. And at right angles to the surface of the road, you have your reaction force. Okay, so the reaction force and gravity force are not in a straight line because the surface of the road is not horizontal, but it is banked. Now, in addition to that, there is also friction force, and friction acts along the surface of the road towards the center of the circle. So let's look at what are the vertical and horizontal forces. Now these will have to be, some of them will have to be components of the reaction and friction force. So let's look at the vertical forces up. So the vertical force up is the vertical component of the reaction force. Now, if you resolve the reaction force into the vertical and horizontal component, you get your right angle triangle. That's a hypotenuse. This angle theta is the same as the angle of banking. And so your vertical component of the reaction force is Fr cos theta. Okay. Now, what are the vertical forces acting downwards? Now, the object is in vertical equilibrium because it is not going up, neither is it going down. So vertically, it's balanced. It's going horizontally. It's not doing that. Okay. So you have your gravity force, which is mg, but you also have the vertical component of the friction force, which is actually pushing whatever it is, the car or the bike, into the ground. Okay, so it's two forces. Now if you look at this little green triangle, so this green line here is the force of friction. I have resolved the friction into its vertical component going downwards, and the horizontal component pointing towards the inside of the circle. Now this angle theta here, this little angle, is the same as the angle of banking, and this is your opposite, that's the hypotenuse. And so the vertical component of friction is Ff sine theta. So if you look at the vertical forces, the vertical force upwards is Fr cos theta, and the sum of the vertical forces downwards is mg plus Ff sine theta. So now, and these are equal. Now the reason why you have this is if you know what is the size of the friction force, if you know what is the mass, and you know the angle of banking, it is possible to find the value of Fr, which is the reaction force. Okay, and the reason why you need that is because you want to know what is Fr sine theta, which contributes towards the centripetal force. Now the centripetal force is actually contributed by the horizontal component of your reaction force, this one here, which is Ff sine theta, because that's your opposite, that's your hypotenuse, there's your theta, as well as the horizontal component of the friction force. Now the horizontal component of the friction force is adjacent for this angle, that's your hypotenuse, that's your adjacent. So your horizontal forces, which contributes towards the centripetal force, is Fr sine theta, which is this one here, and Ff cos theta, which is that force there. So that's how you solve these problems on circular motion where there's friction involved. And if there's another step asking how fast is it going, so once you've calculated your centripetal force, then you go centripetal force is mv squared over r, and once you know this one and you know the radius and the mass, you can get your value for v, okay, by substituting and rearranging that equation. So I hope that helped. Bye for now.